Welcome back. Today I propose to talk about portfolio risk and then the mitigation of portfolio risk using index futures. But before we get into that, let us talk briefly about what we did last time. Last time we arrived at the optimum number of contracts, the optimal hedge ratio, and therefore the optimal number of contracts that have to be taken in the futures market to hedge a particular exposure in the spot market. As you can see on the slide, the value of the exposure is I, and the change in value of the exposure over the hedge period is shown by delta I, which is the quantity in the spot market, the exposure quantity, and delta S is the change in spot price, which is the stochastic variable, and similarly delta F is the stochastic variable representing the change in price in the futures market. We work out the variance of the combination using the expression for the linear combination of random variables, and we arrive at this expression. Differentiating with respect to the degree of freedoms that we have, which is QF, which is to be determined, we arrive at the optimal hedge ratio. Just to recall, the hedge ratio is given by QF upon QS, that is the exposure in the futures market to the exposure in the spot market, the position that you take in the futures market for hedging to the exposure that you have in the spot market, QF upon QS. And the number of contracts is obviously obtained by QF divided by the lot size Z. One more thing, in the special case of a minimum variance hedge, if we adopt a hedge with the prescription that the variance is to be minimum, we arrive at the conclusion that the hedge ratio should be the regression coefficient of delta S on delta F, changes in spot prices vis-a-vis the changes in futures prices changes being the independent variable and spot price changes being the dependent variable. We also then concluded that for the ideal hedge or the perfect hedge, if we want to achieve a perfect hedge, we should have a correlation of plus minus 1 between the changes in prices in this spot market and changes in prices in the futures market. If rho is equal to plus 1, we take the opposite position. For a long underlying position, we take a short position in the futures market and vice versa. Then even if the correlation coefficient is plus 1, we may be required to scale the quantities in the spot market and futures market as per the fluctuations that we have as per the requirements given by the hedge ratio. H in that case will be equal to sigma S upon sigma F, and which will determine the quantity in the futures market that you require for hedging. In the general case, when rho is not equal to plus minus 1, for example, if rho is equal to 0.80, 6.60 or anything, then this implies that only 80% or 60% of the fluctuations can be hedged, and therefore, the minimum variance hedge ratio is computed with respect to this component of the risk of the standard deviation of the spot prices. For example, if the spot prices have a standard deviation of sigma S, then only rho sigma S is the factor, is the quantity that rho sigma S is the proportion of the total risk that can be hedged, and the minimum variance hedge ratio is computed according to the rho sigma S that is to be hedged. The remaining part of the hedge of the risk will not be hedgeable with this particular underlying, because there is no correlation between the prices of the exposure and this particular hedging instrument to that extent. If there is an 80% correlation, then 80% of the variation of the standard deviation of the exposure prices will be hedgeable, and the remaining 20% will remain unhedged if you use that particular hedging instrument. That is the emphasis. And there is a very important caveat here. You see, when we talk about hedging, we are talking about the future. We are talking about annulling the fluctuations in the prices of the exposure by taking an appropriate position in the futures market. Futures market and the process is forward looking, forward oriented. Therefore, the inputs that go into the determination of the hedge ratio should ideally be the forward looking inputs. In other words, what I am trying to say is that rho, sigma s and sigma s, these are the three inputs that contribute to the calculation of the hedge ratio. These should be forward looking. They should be in the ideal scenario, the sigma s, sigma f and rho should determine, should be the correlations and the standard deviations of the spot prices, futures prices, which are likely to occur in future. However, this is practically not possible, and these quantities, the statistical quantities, parameters are invariably premised on past data. Therefore, the underlying presumption is that the past events or the past history is going to replicate itself in future. To what extent that is true or not is a question which the hedger must keep in mind when he takes up this hedging exercise, because if you use the past data blindly without actually understanding or analyzing whether that particular data is going to be relevant for the future. For example, the environmental conditions may have changed since when the data was collected, or to what the period to which the data pertains, and the period to which the data is being used for hedging. So, if there is a significant, if there is a material difference in the environment, then cognizance has to be taken of the change in environment, and therefore, we need to adjust or modify the past data to take account of this changes in environment, because past events may not be replicated in the future, as a result of which the data that we are using may not be representative of the future course of events. Okay, so to start with today's discussion or today's lecture, I shall initially talk about portfolio risk, then we will move on to the CAPM model, and then we will talk about mitigation of the risk embedded in portfolios using stock index futures. So, let us start with the Markowitz mean variance model. We will graduate on to the CAPM model, and then we will talk about index futures. The fundamental premise of the Markowitz model is that investment decisions are made on a two-dimensional framework. The standard deviation representing the risk of the investment, and the expected return, which is believed to be a function of standard deviation. This is the risk return framework on which investments are analyzed. Let us start with a simple two securities case. Both securities are risky. So, if A and B are the two securities, we have the three set of equations here. The first equation represents the fact that the expected return of the portfolio is the weighted average of expected returns of the constituent securities. The second equation represents the variance of the portfolio consisting of the securities A and B as per the expression that we arrived at earlier in terms of the linear combination of random variables. So, that is x A x 1 square sigma 1 square plus x 2 square sigma 2 square plus 2 rho x 1 x 2 sigma 1 sigma 2, and then of course, the weights must sum up to 1. So, we have three equations, and basically we have two degrees of freedom x 1 and x 2. We can eliminate both the degrees of freedom, and we arrive at an expression, we arrive at an equation of the form E of R P, let us call it y, is equal to some function of sigma p, which we call it f of x. In other words, in the two dimensional framework that we are talking about, y representing expected return, x representing the standard deviation, we have a curve representing the combinations of these securities. Now, there are two important points here. Number one, that only those portfolios are possible which lie on this particular curve. We shall explore the geometric structure of this curve in a minute, but first thing is that only those portfolios or those risk return combinations can be achieved by using this pair of securities which lie on the particular curve. This is one fundamental important thing, that we cannot cover the entire plane of risk return space by using combinations of these two securities. We can only cover the curve that lies as per this functional dependence. And number two, there are every point on this curve corresponds to a unique combination of these two securities A and B. So, these are two fundamental features, every point corresponding to a unique combination of A and B, and number two that we are the portfolio possibilities curve is a curve, and only those points that lie on the portfolio possibilities curve can be achieved by linear combinations of these two securities. Now, the actual expression for the portfolio possibilities curve can be obtained if we eliminate x 1 and x 2 between the previous set of three equations. We can do that. There are three equations, you can eliminate two unknowns x 1 and x 2, and you arrive at a relationship between x and y, which is of this form. It is a slightly extended equation, but this is what the equation is. Now, this is, if you look at it carefully, it represents a hyperbola in risk return space. So, the geometric structure of this curve that we were talking about, the portfolio possibilities curve, is a hyperbola. Of course, you can see it in the diagram as well. This is the portfolio possibilities curve, this curved locus represents the portfolio possibilities curve. Here we have 100% of A, here we have 100% at B, and this is the region along which mixtures of A and B, linear mixtures of A and B will lie. Now, there is another important thing. For rho equal to plus 1, there are two limiting cases. For rho equal to plus 1, that is when the two securities A and B are perfectly correlated, this portfolio possibilities curve flattens out to the line AB, this particular line. And if rho is equal to minus 1, then we have a pair of lines which are represented by this, A joining the y axis at a point F, and then B joining the y axis at the same point F. So, the triangle on the pair of lines AF and BF together represent the scenario when rho is equal to minus 1, that is, they are oppositely correlated, and rho equal to plus 1 is given by the straight line which joins the two securities A and B. I reiterate, every point in this is a unique combination of A and B, and number two, only those combinations of risk return are possible which are represented on this curve. So, let us go back to this for a minute. So, what do we have here? We have, let us take a point here. From this point, suppose I draw a straight line here. Now, these 2 points, let us call it x and y. These 2 points are having the same risk, but they have different returns, and it is very clear that the return of x is greater than the return of y for the same level of risk. So, it is again clear that all investors would invest in x and none of the investors would contemplate investing in y. Right. So, similarly, therefore, what we have is, if we have this point is called M, this is the point of minimum variance. at this particular point, given securities A and B, there is a unique combination such that the variance of that combination x A plus x B in a certain proportion has the minimum variance. Now, all points that lie above the point of minimum variance constitute what is called the efficient frontier, and all investment activity would lie on the efficient frontier, that is above the points above the point M along the portfolio possibilities curve. Point lying below M on the portfolio possibilities curve will be dominated by points lying above along the same vertical line, right. So, how do we now determine which portfolio is optimal for a particular investor? Now, we have arrived at the various possible combinations of portfolios, combinations of A and B that result in possible portfolios, and we have also arrived at the efficient frontier, that is the portfolios which are superior to any other portfolio in terms of this having the same return or having the same level of risk, and that is represented by this blue line starting from this is my point M and it continues onwards towards, let us call it point A. Where exactly the investor is going to invest on this curve M A will now be determined by the risk tolerance of the investor, and that is embedded in this indifference map which is being placed over this particular portfolio possibilities curve. The point or the curve, the indifference curve which is highest and which is tangent to the efficient frontier, the curve M A, I repeat, whichever indifference curve lies at the highest point and is tangent to the curve M A would be the appropriate investment at the point of tangency, let us call it P. So, P would represent the combination of A and B that is appropriate for an investor whose risk tolerance is represented by this indifference map. So, we superpose the indifference map on the portfolio possibilities curve, identify the curve which is tangent to the efficient frontier, and the point of tangency will give you the portfolio that is appropriate for that particular investor. So, that is how the two security case evolves. Now, before we proceed further, we need to understand what happens if one of the two securities is a risk free asset. I started with both the securities being risky assets. Now, what happens if one of the securities is a risk free asset? In other words, we are trying to now construct a portfolio which consists of one risky asset and one risk free asset. In that situation, what happens is we have a portfolio possibilities curve which represents a pair of lines of the form which is given here. Let A be that particular security and let F be the risk free asset. Then AF and then the mirror image of AF about the line parallel to the x axis will be the portfolio possibilities curve. Let me try to explain it. At point A, we are having completely 100% of the risky asset A. As we move from A to F, we are investing partly in the security A and partly in the risk free asset. At point F, we have invested the entire amount, whatever our investment amount is, we have invested the entire amount in the risk free asset and 0 in the risky asset A. Now, moving along A beyond A means we are borrowing at the risk free rate and we are investing in the security A. So, at A 100% is invested in the risky asset. As we move from A to F, part of it gets invested from the risky asset into the risk free asset. So, we have a combination of the risk free asset and the risky asset along EF. At F, we are completely invested in the risk free asset, no A is there, and beyond A, we borrow at the risk free rate and we invest in A. What happens along this particular line? Along this particular line, we simply short A and invest in the risk free asset. So, we simply we borrow A, short sell in the market, we get some money, and that money we invest in the risk free asset. That is what this line represents. This particular line F moves sloping downwards. So, if we have two risky assets, the portfolio possibilities curve is a hyperbola, and if we have a risky asset and a risk free asset, we have the portfolio possibilities curve is no longer a curve, it is a straight line. Now, we modify it a bit. What happens if we have two risky assets and the risk free asset? Now, let us split it up into two parts. Let us first talk about two risky assets. The two risky assets are A and B. The two risky assets, all combinations of A and B will lie along this hyperbola AB. Of course, it can be extended if short sales in A and B are allowed. For example, a point beyond A, for example P, would represent short selling of B and investing in A. Similarly, a point Q beyond B would represent short selling of A and investing in B. So, if short selling is allowed, then the arms of this hyperbola will get extended indefinitely. That is one thing. The second thing is, all these points that lie along this represent linear combinations of A and B. Some part in A, along this hyperbola you take any point, along this hyperbola. Let us say you take this point, this particular point, then this particular point represents a linear combination of A and B, some portion of A, some portion of B. What happens? So, this is as far as the two risky assets are concerned. What happens if I now add a risky asset? Let me call this a point, let me call this point C. I have got a point C, I have identified it arbitrarily and it comprises of A and B. Now, I add to it the risk free asset. Now, when I add to it the risk free asset, the combination will be a straight line like this. The region between F and C comprises of what? It comprises of C and F both long, some portion in F, some portion in C, but remember C comprises of A and B. So, we have A, B and C in some proportions along the straight line F, C. And what happens beyond C along the straight line? You start borrowing at the risk free rate and you start investing in C. So, this is how any point in this region can be achieved by using a combination of A, B and the risk free asset F. Suppose you want any point, let us say you want to achieve a point D in terms of risk and return, you can simply join this F and D. You join F and D, let us say it intersects the curve AB at E, then D is simply a combination of borrowing of at the risk free rate and investing in E. So, that is the way you can achieve any point along this region. Now, the question, this is the portfolio possibilities region. Now, we come to the question. That this being the portfolio possibilities region, what would be the efficient frontier? In other words, what are the best possible portfolios that we can recommend to the investor, out of which he has to make a selection? Let us look at that problem now. So, instead of going for C, if I go for P, then any point on FP is superior to the corresponding point on FC in terms of the same level of risk. I get a higher expected return. Similarly is the case with D. So, what am I trying to say? What I am trying to say is that as I move, as I increase the angle theta, I tend to improve the performance or the expected performance of my portfolio, the optimality of my portfolio. Portfolios along FG are better than portfolios along FC or FC extended, and portfolios along FP are better than portfolios along FG. So, what is so special about FP? When do we achieve optimality? We achieve optimality when this angle theta is the maximum possible. Because if it is less than maximum possible, it will be superseded by some other angle which is higher than that particular angle. But can it be this? It cannot be this, because there is no feasible portfolio here. So, it cannot be, let us say it is a W. FW cannot be optimal. Why? Because there is no feasible portfolio here. So, what is the conclusion? The conclusion is that in order that FP be optimal, or we have that optimality condition met, FP must be tangent to the set of risky portfolios. I repeat, we want that FP should be tangent to the set of risky portfolios, to the locus of points of the risky portfolios. That particular P at which FP becomes tangent to the locus of the risky portfolios will give me the optimal portfolio. So, my condition is for optimality is maximize angle theta, provided subject to the condition that I have at least one point in common with the feasible set of portfolios, and in fact, it will turn out to be just the one point in common, and that point will be the tangent point. So, maximize theta such that FP turns out to be the and in fact, the maximization itself will ensure that this FP is tangent to this particular hyperbolic curve. Now, in the first quadrant, as you can see, tan theta and theta are monotonic. So, if you are increasing theta, you are also increasing tan theta. Therefore, you can also state the optimality condition as maximize tan theta. And what is tan theta here? Tan theta is nothing but Rp minus Rf perpendicular upon base, and what is base? Base is nothing but sigma p. So, this is what is the requirement for optimality. Maximize this expression, and this expression is called the Sharpe ratio. So, the optimality condition as per this particular framework works out to maximize the Sharpe ratio, at least in the 2 security plus risk free asset framework. I repeat, the efficient frontier is therefore the straight line. The efficient frontier is therefore the straight line Fp, which is tangent to the hyperbola given by the set of risky assets. Now, let us extend this framework a little bit. Let us now talk about 3 securities. We have talked about 2 risky assets plus a risk free asset, and we have arrived at the conclusion that our requirement for optimality is that maximize Sharpe ratio, where Sharpe ratio is given by this expression. Please note, this efficient frontier in this case, in the case of 2 risky assets plus 1 risk free asset, is a straight line. It says, and where on this particular straight line, where would the actual investment lie? Let us say whether it is at this point or the point P or a point here would be determined, as we did earlier, by superposing on this the indifference map of the investor, whereupon we can decide which particular indifference curve happens to be tangent to this efficient frontier f p, and that would determine that point of tangency between that indifference curve and f p will determine the optimal portfolio for that particular investor. So, this is what the security set is providing you. The risk return preferences are embedded in the indifference map. When you superpose the indifference map on the optimal or the efficient frontier, you end up with the solution to the portfolio selection problem. Thank you. We will continue after the break.